guys, it's Mike from A3Academy, and today I'm going to be talking about gravity. Gravity is a pretty important concept in physics. It's used a lot in different types of problems. So let's get started. So here you see the Earth and the Moon. One thing we know about the Moon is that it's in orbit around the Earth. Now, Isaac Newton wondered what kept the Moon in orbit around the Earth. He thought that there must be some force that kept these two objects together. If there wasn't this force, then the Moon could just fly off into space. But since that doesn't happen, something must be holding these two together. Newton concluded that there was a force of gravity acting between these objects. And basically he discovered that gravity is what keeps objects in orbit. Now, one thing to notice is that the Earth and the Moon exert equal forces of gravity on each other. Now, we know that this is true because if it wasn't, let's say if the Earth was pulling the Moon stronger than the Moon was pulling the Earth, then that means the Moon would gradually get closer and closer to the Earth and they would eventually collide. And since that doesn't happen, that means that the two forces are equal. Newton discovered a couple things about gravity. First of all, he found that the force of gravity is inversely proportional to the distance between the objects squared. Now what this means is that the farther two objects are apart from each other, the lower the force of gravity is between them. Another thing Newton found is that the force of gravity is directly proportional to the product of the two masses of the object. This makes sense because if you have two really heavy objects, the gravity between them is going to be a lot stronger than if you have two really light objects. So from these conclusions, Newton found what we now call Newton's law of universal gravitation, and that is that the force of gravity between two objects equals g, which is a constant, times the product of their two masses divided by the distance between them squared. And g, as we know now from experimentation, is 6.67 times 10 to the minus 11th, with units of Newton meters squared per kilogram squared. Let's take a look at a problem involving this equation. So let's say you have two people sitting on a bench. They weigh 50 kilograms and 75 kilograms, and they are sitting 0.5 meters apart. Now, if you just look at the equation, this is a pretty simple problem. Because if we write down what we know, which is G, R, M1, and M2, we can just plug those into the problem. So we know that G equals 6.67 times 10 to the minus 11th, R is 0.5, and M1 and M2 are 50 and 75 respectively. And when we plug that into the equation, we get that the force of gravity between the two people is 1.0 times 10 to the minus 6 newtons. That's a very small number, but it shows that gravity does exist even between two people sitting next to each other. Now, you definitely won't notice this force, but if this were on a larger scale, the force of gravity is certainly noticeable. Another application of Newton's law of universal gravitation is the force of gravity on an object on Earth. We can use the equation to find a more simplified version of the force of gravity. So we know that the force of gravity on an object on Earth is just the mass of that object times the acceleration due to gravity. And we can actually cancel the mass of the object from both sides here, and what we're left with is that the acceleration due to gravity is g times the mass of the Earth divided by the radius of the Earth squared, where g is again 6.67 times 10 to the minus 11th. So let's take a look at an example where we need to use this equation. Let's say there's a hiker on top of Mount Everest, and we want to find the force of gravity acting on that hiker. Now you might think that this is just 9.8 because that's the accepted value for g. However, you need to take into account that Mount Everest has a certain height. So the force of gravity on Mount Everest is not going to be the same as the force of gravity at sea level. We have our equation, which is g times mass of the Earth over the radius squared, and we know that the radius, which is the distance between the center of the Earth and the top of the mountain, is actually the radius of the Earth plus the height of Mount Everest. Now, if you look these values up, you'll find that the mass of the Earth is about 6 times 10 to the 24th kilograms. The radius is 6.38 times 10 to the 6th meters, and the height is 8,850 meters. One thing you have to notice is that the units for the radius and the height are in meters, not kilometers. When you look these values up on a table or in a textbook, you might see that they're listed in kilometers. However, you have to convert these values to meters because of the units of our constant g. So once you do that, you just plug the values into the equation. It's pretty simple. You end up with 9.77 meters per second squared. You can see that this value is just a little bit less than 9.8, which is the value at sea level, and that tells you that you will actually experience less gravity on top of Mount Everest than you would in, say, Death Valley or somewhere closer to sea level. So there you have it. That's your introduction to gravity. I'm Mike from A3 Academy, and as always, the more you know, the better you are.